Good afternoon, good evening, and good morning. My name is Simon Bate, and I welcome you to the Scriptorium webcast on XSL techniques for XML to XML transforms. First, a couple of words about Scriptorium. If you didn't know already, Scriptorium provides expert advice on publishing technical content. For our clients, we will provide, some of our services include providing analysis of your content, documentation problems. We will implement a solution to your problems. We can actually apply our implementation and transform your data if necessary, and we can provide training. We are competent, technical, and very friendly. And also, an important point, we are vendor neutral. We don't resell anybody's software, and so that keeps us keeps things easy in terms of relationships with our customers. A bit about me. I like to say I've worked for a bit more than 30 years in technical publications, and 10 years of that as a writer, 10 years as a manager, and 10 years developing tools. I'm a card-carrying tools geek. I just love to program, script, do all sorts of things like that. And one of my mottos is, let the computer do the work for me. So I and the rest of my Scriptorium cohort are based in the Research Triangle area of North Carolina, so in the Raleigh area. A little bit of an overview of what we'll be doing today. We're going to actually start out with a poll and see how many of you are familiar with XML or XSL. And then I will talk about what characterizes XML to XML transforms, contrast them to XML to output transforms. And then we're going to divert a bit. You'll get a little bit of ancient history here and some discussion about papyrological data. And then some of the examples I'll show of what some of the things we did or some of the lessons we've learned in terms of XML to XML transforms I will draw from our experience processing papyrological data. And you'll learn what all that means in just a little bit. So, well, why don't we go to the polls? First off, I'd like to know how many of you are familiar with XML. And let me launch the poll here. And you'll see on your little dialog box here how many of you are, so how many just barely know what XML is? How many have heard of it? How many of you are familiar with the basics? Use it regularly or consider yourself an expert? And we're up to 96%. And I'm going to give it just a hair longer. And why don't I call that, that's close enough, I'm going to call that closed. And so just to share this with you, so actually, this is good for me because 44% of you are familiar with XML and 52% of you use it regularly. 4% consider yourselves experts. So that's great. I've given this presentation before, and to a very mixed audience. One of the complaints was that I didn't give enough background material, and so I've been thinking about that and trying to prepare some. But of course, that cuts into our time to. And also bores everybody who knows things about XML. So, so I'm glad we can just zip over that stuff. Great. Now, my second poll is, what's your familiarity with XSL? So I'm going to launch this poll, and please fill in the poll results there. Oh, sorry. I think I launched the wrong one. There we go. Now let's launch it. Okay, now the poll's open. And I should be chatting and saying something during this rather than watching the numbers arrive. That way you're aware I'm still here. And these numbers are a little bit more distributed. I'll give a few of you a little bit more time to respond and see the numbers. but I will draw that at 96%. Since 96% of you responded to the first one, I will mark this poll as closed, and thank you for voting, as it were. Sharing the results. As I said, this is a little bit more distributed. 4% of you, what is XSL? Don't know. XSL stands for extensible scripting language. It's a way of extending, or extensible style sheet language. It's a way of processing XML data to generate output. Or in our case, we're taking XML files and processing them to XML files. 27% of you have heard of XSL but aren't quite sure what it is. 58% of you are familiar with the basics. 8 moderate abilities, 4% expert. So that's a more interesting distribution, and so I'll spend just a little bit of time talking about XSL basics. All right, so let's get this on the road. So let's start out with our typical XML document, and here is an XML document. It's my very small music collection. Here I have in the Oxygen XML editor, which is a marvelous XML editor, by the way. If you haven't used it, it's one of our favorites. Here we have in Oxygen the same thing. I've added one more listing to this, but essentially it's an XML file that contains a music collection. It illustrates most of the things you'll find in XML files. So I have here a music element containing album elements. These the album elements have an attribute. There are child elements of the album. There's some text here. So here we have a title, and there's actual text inside this. I also have here a comment and a processing instruction. Processing instruction is added by other tools for doing processing outside of standard XML things. When you put things in as a processing instruction, the entire syntax within the processing instruction is entirely up to your application. This is entirely fictitious. It was just an idea of a music manager, and it just said that this title had been added automatically. So that's the type of thing you might find in a processing instruction. A little bit more familiarity with that. FrameMaker uses processing instructions in its DOCTYPE implementation for describing for saving information about the FrameMaker conditions and things like that. So there's another idea of where processing instructions are used. Now, about the XML file. Well, of course, we all know that XML files need to be well-formed and valid. And so, as I said, we've got elements, we have attributes, we have some text. This document is also valid. It validates against a DTD. So everything, the structure in this document is described by this DTD file, which describes the content model of my XML file. So I can take this file and say, let's validate it, and our validator says, yes, this document is valid. Now, to a parser, say like XSL, the parser sees this document, this XML file, as a series of nodes. And so each element can be seen as a node. So this music element in its entirety is a node. An album element, this is a node unto itself. But also nodes include, well, nodes are the elements, the text. And so the text here, as this title, that is considered to the parser a node. Processing instruction is a node. And so what this means is in XSL, I can actually handle these processing instructions myself and do special processing if I needed to. Comments are also nodes. And so this is an important thing to remember when we get into doing XML to XML transforms, that all of these things are nodes and they can all be handled by XSL. Of course, the elements do have attributes. And each node here in our document, we say that it has both content and context. So a node, this say this album node, has content. That it contains 2 child nodes. Those are its content. But its context, it has relationships with all of the other information around it. And so this album element is the child of the music element. It has children itself. So, and it also has siblings. And we can talk about ancestors. So there's all sorts of relationships. And this is important in XSL because in XSL, well, XSL, the language itself, is based mostly around a concept called XPath expressions. An XPath is quite similar to a DOS file path, or a file path in any computer file system. The file path allows you to get from any one file or directory to any other file or directory in that system. The XPath allows you to do the same thing. And the XPath is used greatly in XSL for traversing the document or finding information from any one point, or finding a specific piece of information given any starting point. So I could start here at this title element, and I could create an XPath expression, and I could say, show me all of the other title elements. Or I could say, find my ancestor. And the XPath syntax itself is fairly consistent with file systems, and so we use a slash to identify the root of our document. We just use to specify the name, so that to name an element. So we'd say X. This would give us the element named X. We can also use the slash for indicating a child relationship, parent-child relationship. So this expression says, show me all Y elements that have X as their parent. We can also use another shorthand, the asterisk. The asterisk says, show me any element. In XPath, there are a whole series of keywords, and these are called axes. And the axis is a way of accessing from any given point, finding the relationships from any given point. So you can say, use the axes and say, show me the preceding siblings, show me the following siblings, show me my ancestors, show me the children, show me descendants, and so on. Also in XPath, we have predicates. The predicate is a useful tool because it allows us, say, if we have a series of X elements, this will show us the third X element. Predicates can be seen as having a dual use. In addition to putting a number in the predicate, we can also put a Boolean expression within the predicate. And so in this expression, we can say, show me all X elements where the color attribute has the value red. So, so you can see XPath is a very useful, expressive way of describing what might be in an XML document, or finding your way around an XML document. So, XSL itself, well, the first thing to say is XSL is XML. So we use XML to write XSL, and XSL is nothing more than a series of templates. And so we have, I'll show you half on, half off here. We can show a simple XSL template here, and I'll have this on the side while we talk through it. So the simple idea of an XSL template is we start with the root element in our document, and then based on that root element, we then look at all the other elements that are in the context of that element, and we do certain processing based on what those elements are. Then for each of those elements, we can then say, go and look for a template that handles a specific element. Let me start that again. So we might start in our root, and we can say, I need, well, let's start this way. The XSL style sheet is a series of templates. Each template says it handles a specific thing within the XML document. So here we have a template that handles the root element, so it's just a slash. Here we have a template that handles the music element. The basic idea in XSL is you take the current context, you take all of the nodes, or in this case, all of the elements in the current context, and you look for a template that will handle that element. So when we start off, we start at the root and we say, we've got a music element. Can XSL find a template that will handle the music element? And here we have it. So here's a template. It says match music, and all it does, in this case, all this template does is it says apply templates album. And what this means is take all of the album elements in the current node set, in the current context, and look for a template that handles album. So we're here in music. We take all of our album elements, and then we look for a template that will handle those album elements. And here's the template. And let's move on a little bit more. And so this album template then does just a little bit more. This uses the XSL value of element, and what value of does is it returns a string or a value of a particular expression. And in this case, the expression is I'm putting together a string that consists of the contents of the title element, that's a child of album, then the string by, and then within the artist element, I want to find the name attribute, and then a parenthesis, the media attribute, a parenthesis, and finally a carriage return for good measure. So what I'm doing, I'm looking for, given an album, I'm looking for a title, the artist name, and then the media. And I'm going to produce output for that. So actually here in Oxygen, I can run this transform. Let's click here. And so as you can see, we went through our XML file and we generated our titles, the string by, the artist, and then the media. Now, this is an example of processing XML and generating output. Now, I see the world two classes of XSL transforms. And the first is this one, XML to output. We're generating output. The second one is doing XML to XML transforms. And the idea of an XML to XML transform is, in many ways, the promise, or one of the promises of XML, and that is that given an XML file, I or somebody else can write a transform that can extract or reformulate or modify that XML file and generate another XML file, which then can be processed by somebody else. And they might want to use that for output. They could use it for any number of things. So we have XML to output, and the prime use here is generating deliverables. So we might be doing XML to output, we might generate HTML. Or in this case, XML to XML, usually what we're doing is we're modifying the organization of the file, or we're modifying the content of the file, but the file that we're getting on the output end is going to be useful for something else. And a typical example of the XML to XML transform might be you've got documents in DocBook format, and you want to transform those to DITA format. So that would be an XML to XML transform. Now, between the two of these, XML to output and XML to XML, there are differences both in the coding style and the point of view you need to take while you're writing those transforms. And that's a lot of what I wanted to talk about today. So typically when we're processing XML to output, as we are with this one I just demonstrated for you, we're usually looking for elements to process. Now, in a lot of the discussion here, I'm going to say usually or commonly. There's lots of rules and exceptions to this. You might be able to use some of the principles for XML to XML in XML to output, and vice versa. But these are gross generalizations, but they do hold some truth. I'm not saying that. So in XML to output, typically what we do is our XSL addresses elements. We're here saying select the music elements, or here's a template that matches the music elements. Here's a template that matches the album element, and so on. Often in this processing, the processing that we do is most often determined by the ancestors of the current element, of course the current element type or name, and the current element attributes. Now, of course, there are other things may affect the processing, but this is the typical way things work here. And in an XML to output transform, typically what we'll do is we might encounter an element and we'll output some markup. So we might put out an HTML H1, for instance. We might output some boilerplate. So we might say something like section and a colon and a space. And then, depending on the child elements of the current element, or the child nodes, we might output some content from the XML. So there might be text within the current element, and we might want to output that. Or if there are child elements, we may want to process those child elements. And of course, that way we use apply templates to say, take the current set of elements and go find templates that match these elements. Another important thing about XML to output is we can selectively ignore elements and content. So in the transform here that I showed you, let's go to the XML file. We'll notice that we have the media attribute. Our artist has both a name and a genre attribute, and we have the title. But in this transform, we really had no need for saying anything, sorting anything by genre, and so we chose not to output anything about the genre. And because of the nature of these transforms, we can opt to do that. This time around, I decided not to have the genre. In another transform later on, I could. And one of the principles there is that usually from XML to output transforms, the output you can consider as disposable, or you're going to be running this transform many, many times in production. So I might run a transform, take my output, hand it off to a customer. I might run another transform, or run the same transform on data another day, and hand that output to another customer. And so I can do that all day long. So let's look at XML to XML transforms. One of the first shifts you'll find when you're doing XML to XML transforms is your templates, as a rule, rather than addressing elements specifically, you address nodes, because the nodes are a way of describing everything in the document, in the source XML document. So you're not just interested in an XML to XML transform. You're not just interested in transforming the elements. You want to copy everything over. And there's the key word that I haven't been saying yet, and that's one way you can think of an XML to XML transform. An XML to XML transform is a copy of the document that includes some additional processing. Now, in addition to the ancestors and attributes, we're also going to be interested in looking at the siblings and the descendants of the current element. These often have as much, if not more, weight on how we're going to choose to do our processing as the current element or its ancestors. So the actions that we take, instead of generating boilerplate and then going and processing children and so on, what we'll often do is copy the current element. Our template might reorder some elements, or we might actually create new elements. And then one of the big keywords, often when you're doing XML to XML transform, you want to preserve everything because you've got a document contains a whole bunch of information, and you want to be sure that the next person to take that document is going to still have all of that information available in your output document. And so this sort of turns the equation around in a way that you can say that in some ways the source is disposable because, again, you run an XML to XML transform perhaps once you actually get it really working. You run it, it's done, it's transformed its data, so your source file is now old news. It's no longer necessary to you. It's the output which is the interesting thing. So some of the characteristics of the actual processing that we do in XML to XML transforms. One of the main things that that we use in an XML to XML transform is called an identity transform. And if there's any single piece of information that may be useful to those of you just getting familiar with XSL, this is one of the most important things. Also, in XML to XML, what we do a lot is what we call a look-ahead operation. So we need to look at what's coming up. What are the children? What are the descendants? And what's in there, because, as I said, sometimes the content of the children is going to influence how you process your data. And as I've said before, you want to preserve everything, lose nothing. And what follows from that, of course, is when you're doing these transforms, and particularly in a production environment, you need some form of quality control. You need to ensure that you really are processing all of the data and processing it accurately. And of course, the greater the volume of data, the more difficult that becomes. And of course, we haven't really talked much about the DOCTYPE. The DOCTYPE declaration in our XML file is what told the parser or our validator which DTD file to use, or it told us what the information is within this document. Sometimes when you're doing XML to XML processing, the DOCTYPE is going to need special handling, and we're going to look at all of these in the next several minutes. So let's talk first about the identity transform, because as I said, that's probably the most important thing. So here we have an XSL style sheet. It's a little bit different than the one that we saw before. I didn't really talk about it, but the previous one, it said the output method was text because we were just outputting text from it. In this case, we're saying that our output is going to be XML, and this actually tells our XSL processor when you generate output, then you want to output an XML, output an XML header along with an encoding type. Now, the first thing we do here is we match the root template, and instead of naming any specific element, and you'll notice that there are no elements named in here, what the identity transform does is it says, let's apply templates to anything that's an attribute or any node. And so the bar here is an or sign, and the node is a way in XSL of describing matching any node. So this template, or this apply templates, puts everything in orbit, as it were, and the transform engine looks for the template to handle it. The single other template that we have, that doesn't make sense, does it? The other template in this style sheet matches on any attribute or any node. And all that this does is it uses the XSL copy operation. So whatever we match on, if we matched on music as an element, the music element as one of the nodes, and it would copy that music element. And then within the copy, what we do is we say recursively, let's apply templates on select any attribute or any node. And so what this does is it recursively, that is cyclically. It processes everything from the root of the document down to the very last element or the lowest level element in the document tree and copies everything to output. And we can actually see that. Hang on a second. So we can actually see that here in Oxygen. Here we have our very same identity transform. And we're going to run it on our by album XML file. So if I click here, it'll run it. And if you notice that now the output here is exactly the same, minus the DOCTYPE, of the output that the output here is almost exactly the same as the input file. So that's our identity transform. So the identity transform, as I said, it makes a deep copy. That is, it starts from the top and it copies all the way down to the bottom until it runs out of nodes to copy. It copies all nodes. Now, if you're slightly familiar with XSL, you may know that there's XSL copy and XSL copy of. The question is, well, why not use copy of? Well, copy of is fine when all you want to do is replicate the entire document. But you know, we've got file systems for doing that. I can just go to DOS and say copy X to Y and get the same thing done. The reason we want to do the copy of is we want to test the nodes. And so this is where we can actually start into looking for specific elements. But the nice thing is, by basing everything that we do on the identity transform, everything that we just need to have copied just automatically gets copied for us by this transform. When we want to start processing specific nodes, then we can add to the transform, we can modify the transforms, and we can say, oh, well, in this case, do it slightly differently. And so let's take a look at a simple modification. I'm still not looking for specific elements, but what I'm looking for here is nodes. And so you can see I've broken things up a bit. So we still have the same base template. And so the root looks for any attribute or any node. Now I've separated out the attributes. So if you find an attribute, then just copy that attribute. Attributes don't have children, so that's just a perfectly safe thing to do. The next rule is, this is a little bit complicated XPath expression. What we're saying here is match any node that is not itself a text node. So as I said, nodes can include elements, comments, processing instructions, or text nodes. And so what we want to do is, if it's not a text node, then just process it just the way as we've done before. We do a copy, we do an apply templates. The next one down, the next template, the new template that I've added here, now says if you are a text node, and I've added a little extra expression in here because I wanted to make sure this is a text node that is not blank, that doesn't contain any white space. So if you're a text node and you actually contain something, then output a quote, copy the content of the text node, and then output another quote. And so what this is going to have, the effect this is going to have is every one of these text nodes that was just copied by the previous transform, it's going to actually have quotation marks put around it. And we can see that by running the transform. And so now you see we're actually able to touch the text and say, okay, copy everything, but in the case of the text nodes, we want to put quotes around the text nodes. Now, pretty silly example, but it shows you some of the power, some of the discrimination that we can use when looking for specific things in an XML-to-XML transform. So this was fairly easy to do, fairly easy to write. Another thing we could have done is we actually could test for elements. So we could have said, we could have tested for, say, the artist elements, and we could have reformulated this so that all the information was grouped by artist rather than being grouped by album. But of course, that would be rather complex and would take quite a long time to explain in today's simple presentation. So we'll leave it at that for right now. So let's take a break from XML for a minute, and let me give you a little lesson in ancient history. So let's roll back about 2,000 years, and we're familiar with many of the ancient Greeks and writers like Plato, Socrates. Of course, they were even more than 2,000 years ago. But there was lots of other writing that went on in Greece about 2,000 years ago, and this writing, well, business went on, life went on. People were married, there were marriage contracts, people died, there were wills, people exchanged land, people bought and sold goods, beer, all sorts of things. Business went on, and for every business transaction, of course, as now, there was a document. Now, the documents were written on papyrus, as a rule, and being 2,000 years ago, rather than being cuneiform, as you might expect to see in Egyptian papyri, they actually wrote in ancient Greek because, of course, they were Greek. So now the papyri contained all these, all these Greek characters. They also used pots. Sometimes there was you'd find characters written on potsherds, and this potsherd here will become interesting in a minute. Now, of course, being a legal document, they had to save them away and say, someday this might become useful. Flash to a vision of the end of the Indiana Jones movie in a warehouse full of crates and crates of things. Well, the Greeks did the same thing. They sealed their papyri up in jars and stuck them away. And the Mediterranean is a relatively forgiving place in terms of paper and papyrus, and so a lot of the papyri survived. Now, of course, some of them did get eaten away. This one's eaten just a little bit. The pot, of course, did not survive all that well, but there's a surprising amount of information on the piece of pot. So fast forward 1,900 years to the end of the 19th century. There was a boom in archaeology. People found that there were all sorts of archaeological treasures all around the Mediterranean. And as they found those, they started to find the papyri. And it wasn't long before a scientific field of study grew up around these papyri because people needed to transcribe what was on the papyri. They needed to translate it. They needed to keep data about where it was found, who had done work on it, what was its state, all sorts of information about that. Now, if you're transcribing papyrus, of course, you're going to want to print it in a book and say, this is what I found and this is what I think it says. And of course, when you print, then you have to indicate what was missing or what you thought was there or what should be there. And so over the next 30 years or so, the papyrologists developed a system known as Leiden. And this Leiden allowed them to write out in Greek what they found, but also to indicate where information was missing. And so they had symbols for places where there might be a gap and they knew how much space there was, or they didn't know how much space there was. They could indicate missing letters. They could use parentheses and indicate that there were abbreviations, and they wanted to show what they thought was the expansion of that abbreviation. There might be letters omitted from the original. There might be letters that were actually superfluous. And so the thing we're going to focus on mostly are these square braces, because that's the next part of our story. So the square braces, as I said, show missing information. And so this is actually the Greek that was translated from that small piece of potsherd, or I should not say translated. This is what was captured or transcribed from that. And so here we have what's probably a number, the number 13, and then petos and zoutou keramion, and of course this is an abbreviation, and this is an abbreviation. Keramion is essentially a pitcher of beer. And so here we can deduce from this potsherd, here we go, that Juan Petos either took delivery of or gave delivery of a keramion of beer on a particular date. So tremendous amount of information we can find on these things, but you can see the Leiden in actual use. So then the Leiden existed that way for the next 30 years or so, or 60 years, until computers came along and people started saying, oh, well, let's take all these printed documents and produce and encode it. And of course, SGML was around, and David Packard, who's the son of that David Packard, was instrumental in converting a lot of the existing documents to SGML. As time went by, XML came out, and an Epidoc standard was developed, which is a form of TEI.2, which is used for encoding these XML files. Now, all told, the world's total knowledge of papyrological transcriptions makes up about 55,000 XML files. This is great. A group wanted to take these online, but they found in transforming the SGML, or going to SGML, there were a few conversion errors. So this, the Leiden square brackets didn't get translated all the time, so those needed to be found and corrected. And also, there were a number of errors in the encoding of Greek numbers, and this is where we came in. So the square bracket Leiden indicates missing corrected or interpreted text. And in Epidoc, the XML standard, they use supplied reason lost. And so instead of this DOSC, where the IOSK is actually interpreted, we would have delta and then the supplied reason lost and the iota, omicron, and so on. And so this is how it should look. But the problem is we found there were two types of problems, two types of occurrences of these brackets that were incorrect. First was there were brackets that we knew that if we'd replace these with the supplied reason lost, this would still be valid XML. So that was relatively easy to do, but still, because it's in text, somewhat tough to find. Finding them was actually harder than actually transforming them. And then we had other cases where if we just gone ahead and replaced the brackets, we would actually have invalid XML because, of course, you see if we had supplied reason lost here, we couldn't have the supplied the other side because this would not be nested. So one of the things we had to do here is develop several look-ahead operations. Now, in a look-ahead operation in processing XML to XML, what you want to do is create an XSL variable. And so given a node set, given the current node set, or any given node set, you want to create, you can do a couple things. And you can create a subset of those nodes. So you can say, show me all, make a collection of all nodes of element X. You can also, given that node set, you can return a value. And so you take a node set and you run an XSL transform, and that transform then returns a number, or perhaps a Boolean value, or perhaps even a string. And then you can test on that returned value and see. So one of the things we had to do in numbering is we had to actually see whether an element contained any numbers at all. And so we'd write a look-ahead operation that would go in and look ahead, look down within the children and say, yes, there are numbers within this element, or no, there are no numbers within this element. So as I say, we can test on these, test on the contents of the variable that gets returned. Now, a particular type of look-ahead operation that we created, that we used for this, is something I call a look-ahead map. And the idea of a look-ahead map is you take a complex set of nodes and you reduce that set of nodes to a string that represents the contents of that node. And the idea here is we have one character. The string would consist of one character per node. And if this node set contained an element, I would put an E. If there was a text node, I could put a T. And I can look at a given set of nodes, so say a given set of children of the current element, and say, oh, this is a map of the contents of that node. So I can, whoops. If there were text nodes that contained brackets, I would actually output an open bracket or a closed bracket. If I found a child node, that is an element, and that child node contained brackets itself, I would use a dash. So given a particular XML string, we might have, here's text, here we have an element, here's more text, and here's an element and more text. And so this would result in the look-ahead map TE. Now in the second case, we actually see there's a square bracket here and a square bracket here. And so the map resulting from this is TE and then bracket E close bracket. And so I can look ahead, I can look at this map and I can quickly see, oh yes, there's a balanced set of brackets coming up and I know how to process those. Here we have text, another element, here text containing a bracket, and then there's a nested element, and within that nested element there's a bracket. And so the output from here is TE bracket, then a dash T. And so I can tell from this that here's one of these invalid cases, or if I was to do a simple replacement, it would be invalid. So I had to process that slightly differently. So there are several advantages to using these look-ahead maps. And one way is it's a very quick way to understand the organization of a complex set of nodes. The next is the map returns you a picture which you can then search. So I could search for an open square bracket and then search for a closing square bracket within that same string, or or not. Also, the character position in this map, because I've got one character per node, I can say, oh, in the third position I have an open bracket, and so if I would use node and then the 3 in as a predicate, this would return this expression here would return me that node. And so it was a fast way of accessing the information. Also, it turns out these are very good debugging aids, because I'd use the XSL message element to display the current state of the look-ahead map. And it was interesting to watch processing, because I would see this the string that was output by message, it would get reduced. It would constantly shrink down until it was nothing. I could also tell when I had an error, because the map would sometimes bump up in size all of a sudden, and that told me that there was an error in my processing, because all of a sudden I was taking too big a bite of something. So the solution for this valid form is I'd create a look-ahead map for the child nodes. I'd look in the map for pairs of brackets, and if I didn't find those, I'd then drill down into each of the elements that was in that node set. If I found a dash, I would handle it as an invalid, and otherwise I would go into each of these text nodes, find the bracket, and replace it with the correct output. Every time you drill down, so this first case we drill down, every time we drill down into a new element, we create a new map. So every time we'd see a new map of what's the information within that specific element. Now, I mentioned an important thing was testing the fixes. In this case, these brackets were scattered way throughout everything, and there was just too many to actually go and say, have we done this all? And of course, we're dealing with these 55,000 XML files. They're the entire world's papyrological knowledge, and if we screw it up, then our errors are going to be perpetuated. So we wanted to make sure that we were doing things correctly. And in this case, what we ended up doing was we implemented a spot check thing, where we'd pick randomly 50 most likely files that would contain these brackets in strange configurations. We'd run the transformation and then have the papyrologist examine just those 50 files carefully. We figured that was a large enough set. They'd come back to us and say, oh, you're missing this, and so we'd catch that. And then eventually we had it narrowed down to they couldn't find any error, so we ran the transform and replaced the data. Now the other thing we had to correct had to do with a curious thing about Greek numbers. Just to quickly review, or to quickly talk about this. The Greeks didn't use the Arabic numbers that we use. Instead, they used what they had on hand, which was the characters of the Greek alphabet. So for the ancient Greeks, 1 through 9 was alpha, beta, gamma, delta, epsilon. And here a special character was dropped in, sigma, zeta, eta, theta. So this is how we counted from 1 to 9 in ancient Greek. Now for 10 to 90, we'd actually go iota, kappa, lambda. We'd start on over. We'd go all the way up through 900, where we run out of letters. And so for 1,000, they'd start on the capital letters. Now, after 9,000, or you can imagine you can put together a number 9,999, what happens after 10,000, or what is 10,000? Well, the Greeks called that the myriad. So that's where we get our word myriad. So there's your word for the day. And of course, trying to decipher these things, context is everything. Well, when these files are transformed into XML, or first, well, in SGML to XML, a number might start out 1,234, and the 34 was in the Leiden bracket, so that was assumed. And these numbers were incorrectly grouped into 12 and 34. Then, for some reason, these numbers were reinterpreted in the Greek and reinserted in text. And so what we got was, what resulted was iota beta, so that was 10 and 2, and then lambda delta. This actually should have been capital alpha sigma for 1,200. So what we were tasked with is go in and find all of these numbers and correct them. Now, this is one of those cases where it was very important to do look-aheads and know what the children were, because we could find numbers, and they might have numbers as siblings, they might have numbers as children. There were all sorts of relationships, so it's very hard to find where the numbers were. So we might start out with the Leiden 171. This actually equates to supplied reason lost, num value 17. Here's the iota zeta, and then supplied, and finally the num 1 alpha. And what this really should have been was num 171, and then supplied reason lost rho omicron. So as I said, we had to go in and find these strange nums that were spanned by supplied, and they should have been put together. So that was hard to do. We did it mostly by look-aheads, but the reason I want to talk about this is more our method for the method David Kelly and I discovered for testing the fixes. So what we did was, in our XSL transforms, we actually implemented the transform using a choose statement, or put a choose statement into the transforms. And so the choose said, if you're testing the data, then don't yet really run the transform, but what you want to do is create a wiki table on output showing both the original element and the element as it would be if you'd run the transform. And so, as you can guess, this code that actually produced this modified element, we could then reuse in the final run and process everything and say, okay, here's how it works. But the nice thing here is what we could do, we'd run it first. It would generate this wiki table, which we then posted on the wiki site of the group we were working with. And they could go to the wiki and review this table and see for each of these things. They could see the original and they could see the modified right in, side by side. And it was a tremendous tool for them to be able to go through and look at it and say, oh, you got this one right, you got this one right. Oh, here's a whole bunch of cases where you didn't get it right. And we were able to go through and correct the data that way. So being able to generate output that is usable as an analysis tool is a really useful thing. So how did we structure the code for this? Well, we had essentially two XSL files. We had a report XSL file, which generated wiki output, and we had a transform XSL, and that was the identity transform that transformed most of our document. Then we had a common XSL, and so the common XSL, it did most of the work, and it pulled in the report XSL to generate the wiki output, and then also, oh, that's right. So, sorry, other way around. The report XSL used the common to generate the wiki. Our transform XSL actually did the final transform, and this also pulled in the common. So the common was where the actual transforms I was showing you here, how we got to the modified element. That common one was where that shared code existed. So finally, talk just a little bit about the DOCTYPE. You might not, the DOCTYPE itself does bring up some issues sometimes. Remember, here's the DOCTYPE in our XML file. When you're doing transforms, typically if you're doing data type transforms, you're going to output, you're going to have the DOCTYPE handy. If you're doing XML to XML transforms, it's often somebody hands you the XML files and says, here's a bunch of XML files, or even worse, here's a hierarchical set of files, and there's XML throughout, and I need you to transform those, but I don't have the DTD, but they have DOCTYPEs in them. How do you deal with that? Well, I'm not going to go right into how you deal with it directly, but I just wanted to point out that there are 2 Scriptorium white papers I created. You can go to our site and see these, and one of them is when you're doing XSL transforms, how to ignore the DOCTYPE. Because if this music DTD file didn't exist when I ran any of these transforms, the parser would complain, and I wouldn't be able to get any further. Now, of course, one simple solution is you go to all your files and you delete the DOCTYPE declaration. Now, that's possible in a small set of files. With a Perl script, it might be even possible with a larger set of files. If you're dealing with directories and directories of them, you still might not want to do that. There are other approaches, but the best one is you can actually set up your XSL transform just to ignore the DOCTYPE declaration. And so I have a white paper on our website, as I said, on ignoring those DOCTYPEs. There's also a white paper on how to add the DOCTYPE declaration back in on your output XSL, because as you saw, when we ran this transform, we didn't get a new DOCTYPE here, so we'd actually have to recreate that to put that back in. So, in summary, in doing XML to XML transforms, identity transforms are your friend. Learn about them, use them, practice with them. You need to focus on nodes rather than elements because, of course, elements don't include the text. That's the real key one. But also elements don't include your comments and they don't include your processing instructions. You may need to preserve all of those. Build variables or use lookaheads, create yourself variables, find out what's coming up in the data before you start to process the data. That's a very useful thing to do. You can use lookahead maps and that makes your data accessible. Oh, and by the way, I've also used the lookahead map technique in parsing OpenOffice.org spreadsheets where there were lots of spans. It was a very handy way of looking at a row of data, and I could tell where the cells were and where the spans were, and I could process each row of data very quickly that way. Test your results. Test again, because of course the data that you process may be used, who knows, for centuries, possibly. So, a couple other things here. I will be sending some of these links around following the presentation. Also, following the presentation, you'll be receiving an email with a survey, and we certainly invite you, please fill out that survey and return it. Few resources. If you're interested in the papyrological data, you can find a lot about the project that we worked on, the IDP project, IDP2, at this address. You can actually look up a whole bunch of papyrological information online at the Advanced Papyrological Information System at this address, and I will send those out with the follow-on email. So this ends the recorded portion of our presentation, and I'd like to open the floor to any questions. Let me go to the